afternoon, everyone. We're delighted to have Professor Maurice van Putten from Korea at Sejong University. So he is a theoretical expert on cosmology and gravitational waves. Let me just briefly go over his past career. So he's received his PhD at Caltech in applied mathematics, and then he did his former affiliations starting from Cambridge, and then sometime in France in CNRS, Orleans IAS, and then he moved to Korea, and then he did assistant professorship in Korean Institute of Advanced Study, and then after on he moved to Sejong University in 2012, and then since he's been staying there as a faculty in astronomy and space science department. And then he recently got awarded an academic award for this year from Korean Physics Society on his contributions on gravity and cosmology, as you can see from his title. But today he will be specifically talking about cosmological side, which is about Hubble expansion beyond ΛCDM from Big Bang quantum cosmology. So we're happy to have him. Let's welcome him. And then, whenever we're ready.
Yeah. Well, thank you. Thanks, firstly, to the organizers of this seminar series for this opportunity to say something about some very current work. Actually, that originally I started at KIOS, but more recently we had several developments which are now quite opportune to talk about in context of H-null tension and James Webb discovery of the impossible galaxies at cosmic dawn. So the specific title of this work is here, The Hubble Expansion Beyond ΛCDM in Big Bang Quantum Cosmology. And so the content, the way I organize this talk is to start with some basics. Not everyone, of course, is working on H-null tension, but I'll illustrate this problem as it is being introduced both by the local distance method and by measurements of the cosmic microwave background. And then I'll take a detour through theory in order to formulate an alternative that gives a new solution to the Hubble expansion with no free parameters that then can be used to infer scaling relationships for, in particular, the Hubble parameter as defined by ΛCDM analysis, and as it then relates to, and in fact predicts the Hubble parameter following the theory of expansion in the Big Bang quantum cosmology. And then, of course, one cannot have a complete talk without also saying something about dark matter. So to that end, I'll talk about briefly the James Webb impossible galaxies as it was highlighted recently. So at a very cartoon level, when we are looking at our current ideas of cosmology without any discourse on pre-Big Bang cosmology and multiverses, you're essentially looking at a schematic like this, where you have a Big Bang according to Lemaitre, and that gave rise to the first creation of matter and radiation that then left some acoustic perturbations frozen at the time of the surface of mass scattering. And then as the universe continued to expand, we see what we have today, including the formation of large-scale structure down to galaxies and black holes. Now, theoretically, it seems all the data point at least to leading order to a three-flat universe. And that means that essentially the metric is that of a conformal scaling of Minkowski spacetime. This actually is less innocent than it seems, because you could say it's quite innocent because it's sort of a minimal ansatz, because if you like, Minkowski spacetime is the minimal idea we have about spacetime. But when you talk about conformal scaling of Minkowski, that actually is not in the spirit of general relativity. So already this is a bit of a flag that says you have to be very cautious how you deal with this theoretically. Anyway, the leading order description geometrically, of course, is by the FRW line element, and you can put this under the microscope by performing observations, particularly on the Hubble expansion. Of course, historically it was the other way around. We discovered Hubble expansion, and then based on that, people inferred that there should have been a Big Bang at some finite time in the past. To that end, you can rewrite the conformal scaling of Minkowski into this slightly more familiar form of the line element that explicitly then talks about the conformal scale factor now in terms of the cosmic time t. And if you take the logarithmic derivative, you're looking at a dot over a, and that we define to be the Hubble parameter. Of course, the key question is, what physics governs this Hubble parameter? As I said, you have to be very cautious. Naively, you could say, let's just apply general relativity and go ahead. But the underlying theory of the conformal scaling of Minkowski means you have to be quite cautious in doing that. At any rate, the observations on the Hubble parameter rely essentially on the use of standard candles. But even before introducing standard candles, of course, you have to calibrate them. And the primary calibration starts, of course, with parallax. Parallax essentially has minimal, if not zero, assumptions, and that extends to some distances through which you can calibrate the first standard candles, and then you can go up the ladder. And this is what, of course, people like Maurice and others have developed to very high detail. But essentially and historically, it follows this picture, right? You start with pure geometry, and that gets you out these days to perhaps 10 kiloparsec or so, and with the latest observatories, and it was pioneered successfully only in the 19th century. The idea is very old, it's already from the Greeks, but it didn't really work out that well at the time. And then the next level up is using CFETs because they're quite bright, and they have a very interesting, well-defined period luminosity relation discovered by Leavitt. Well, they're quite bright, but there are brighter sources, namely the type 1a supernovae. And as Phillips showed, they actually allow normalization through the correlation between peak luminosity and the decay time of the light curve. So that basically reduces the scatter in each light curve to practically better than 7%. So if you have 100 supernovae, you will get down to, theoretically, 0.7% scatter. That's the basic idea. So you certainly need many supernovae, but you don't need insanely many necessarily. Because the type 1a are much more bright than CFETs, as you can see, you can gradually move yourself up to larger distances and make a successful measurement of the Hubble extension by combining photometry and spectroscopy, giving you the redshift. And so Reese developed this, as I mentioned, into exceptionally great detail and resolution according to this basically 1, 2, 3 step. And accordingly, every year, every few years, he puts out a new paper with a better, or at least higher resolution measurement. So his latest is that H0, according to this procedure, is 73.04 plus or minus 1.04 kilometers per second per megaparsec. The beauty about this procedure, although as you can imagine, the devil is always in the details, there are a lot of details here because you have to be very much in control of all your statistical uncertainties and potential systematic uncertainties. But one systematic uncertainty you don't have, you're not using any cosmological model. Right, you're simply following the recipe pioneered by Hubble. And so that's the power of this, is that you're just looking at the numbers as is without assuming anything on the physics behind the Hubble extension. Now, alternatively, equally powerful in many ways, of course, is by studying the cosmic microwave background, which also has been increasingly observed by various satellite missions. The last one is, of course, Planck. And you can study this in great detail if you have a model. So in this case, essentially you are using a model-dependent analysis, although there is one feature that is at least in essence, model independent. And that's the angle of the baryon acoustic oscillations. But nevertheless, that's usually extracted by assuming a model, in this case lambda CDM, by the Planck collaboration. And as I was alluding to earlier, by working on parameter estimation in a cosmological setting, you cannot conform entirely to the basic ideas of general relativity because there is no asymptotically flat Minkowski spacetime in this case. Right? There is a Hubble horizon and a finite Hubble radius. So what you do instead of talking about single objects with well-defined energies like the total mass energy in the sun or a galaxy, you now normalize the quantities to dimensionless densities. So that's a fundamental departure from GR, and you can do that by exploiting this well-defined closure density, 3h squared over 8 pi g. And so you get quantities normally labeled omega for all the content that you attribute to the universe, radiation, matter, and dark energy of the vacuum. Now, if you work in the, also because it pans out in the data, but of course conceptually it's also easier, if you work in the idea that the universe as we see today is essentially 3 flat, then the sum of all the omegas is equal to 1. And any numerical relativist will tell you that's essentially the Hamiltonian energy constraint. So at this point, I'm still not talking about any theory other than a proper setup of the parameters at hand. And so next, what Planck did, and up initio any other analysis of the CMB, is typically to use lambda CDM, meaning you assume a constant rho lambda of the vacuum. And then you can do a fit to the power spectrum. The first peak, however, is something that in principle you can fit without assuming lambda CDM. You can imagine using some higher order polynomial to do that. So it's important to appreciate that the BAO angle, ab initio doesn't ask you to assume any model, but practically people do estimate it using lambda CDM. But then by doing that, you do get, of course, a lot of parameters. You not only get the Hubble extension, but you also get an estimate of the matter density, of course, within lambda CDM. So it's important also to realize that this omega m is actually a model parameter. After all, omega m is roughly 30%, but what you observe is only 5%. That already tells you that you should view it as a model parameter. It doesn't necessarily mean that it is not realized in nature. Just ab initio in this procedure, if you were to have a different model, your omega n might actually come out a little differently. Okay, so now you find that through this fit, you get also, through this entirely different angle of approach, a Hubble parameter. And this Hubble parameter is a little different. It's 67.36 plus or minus 0.54. The 0.54 tells you that this is a very serious estimate with very low statistical error. But at the same time then, as you can see from the previous 73, these numbers are not the same. So the leading question you would ask, so which one should I take as a true value? Because presumably we live in a universe that only has one Hubble extension parameter today. Okay, that's known as it's known by various labels. It's known nicely as an H-naught tension, but of course now that it is essentially 5 sigma, people like David Gross would comment, if we found something like this, he's of course a particle physicist, we wouldn't call it a tension or a problem, but we would rather call it a crisis. In other words, it's something to be taken quite seriously.
So the distinction is 5 sigmas, but if you take the errors and add them in quadrature, it's barely 5 sigmas, isn't it?
Yeah, it's barely 5 sigma.
So there's still a tension, even in particle physics, we still call it tension. I mean, that's vocabulary.
Yes, but you can add observations from other channels, and then it kind of tips over beyond. But sure, it makes the discussion more interesting. Do we really have 5 sigma or not? You can say it's a bit academic, but at the same time, it is actually potentially a productive discussion because it pushes you to think, what else can we do? So it's not always silly to talk about the 5 sigma. For instance, there's a whole industry writing reviews on this development, and this discussion is not only in this room, it's in many rooms around the world. Here is a very nice review by Leonora Di Valentino et al. It's a very long list of authors that summarizes in, well, not the most recent, but the very recent 2021 summary, reviewing these various approaches to trying to make sense of this H-naught tension. Of course, when you say make sense, that means theoretically, but also observationally. So, as you can see from this long list here shown, there are many discussions and many approaches to basically putting under the microscope various assumptions in the local distance ladder, and also adding some additional approaches to measuring H-naught, because you can imagine considering different kinds of combinations. Of say, you could even combine the CME that measurement with the supernova measurement, and with or without BAO, and so on and so on. So it's not the purpose of my talk to review this review, just to mention that it's become now kind of an explosive situation that people are really open-minded to consider, basically anything that you can imagine that might hopefully contribute to our understanding. But the problem then still stands, that we have a Planck lambda CDM analysis of the CMB given one value as sort of the starting point for all this discussion, and a estimate of the Hubble expansion from the local distance ladder. And the discrepancy is actually not just quantitative, but also you should appreciate perhaps the sign. It's 9%, and it's plus 9%, meaning the local distance ladder measures the Hubble parameter to be larger than that you get from the CMB. And I would argue that that's important as well. Now, lambda itself has a very long history, the vacuum dark energy, and I'll argue that perhaps we should move into this direction to think about the H-naught tension in terms of lambda. Also because this presents an open question in our understanding of the expansion of the universe in its own right. It started much before even the discovery of a positive lambda, let alone H-naught tension. So already in the early 20s and 30s, people were discussing this in great depth. I found this picture on the web. That's easy to find, but actually if you zoom it out, they nicely were talking about the Friedmann equation, the first Friedmann equation. And on their blackboard, in this discussion between de Sitter and Einstein, you find in the notation of a small lambda the very discussion, although the paper that they were discussing, that they wrote together, was actually on R1, the matter density, but they already mentioned, of course, lambda, the de Sitter, introduced by de Sitter, in this very equation. So this is actually the Friedmann equation, including curvatures, a little k on the left that refers to curvature, but we'll take that to be 0 in the free-flat universe. So the question is that they asked what is responsible for the expansion of the universe. And okay, the text is here written in Dutch, and translated it means who inflates the ball, what makes the universe expand. That does lambda. Actually, nowadays we would say lambda is responsible for the accelerated expansion, not so much for the extension. And then he added to that, there's no better answer. Well, that's a very dangerous statement to make, of course. So what I argue here is that there is actually a relationship between the Hubble parameter and lambda. And you can see that from the following plot, which is actually a plot basically based on basic calculus. It's not obvious a priori why the H-naught tension problem should have anything to do with lambda. I mean, it's certainly a question to be posed, and my argument is as follows. Firstly, if you think about H-naught, H-naught is an extrapolation, right? Because the data we get are from the past. This is very much true, of course, for the local distance ladder. We would very much like to have data on H from the future, but it's kind of hard to get by. So all the data are from Z is positive. And then we estimate the Hubble parameter today by extrapolation of the data from z greater than 0. As you all know from, say, numerical analysis, extrapolation is very dangerous. Essentially, you have to make some assumption if you want to do this model independently, maybe some order of a polynomial or something of that nature, and then extract your data to z is 0. But that will that will be susceptible to the curvature in the graph. And of course, you don't necessarily know the curvature. It's a higher order derivative issue. So you will be opening up yourself to a sensitivity to potentially a systematic unknown, which is what is the curvature in z is 0. Now, theoretically, you can actually introduce now something to streamline this discussion, because practically there are, if you like, three possibilities. Either the Hubble parameter goes to a constant, which means the future is going to be de Sitter, or the Hubble parameter goes to 0, which means that you're going to Minkowski spacetime in the future for who knows what reason. Or maybe there is a blow-up. Maybe there is a big rift or something of that nature, which is also anticipated, for instance, by the swampland conjectures, that the Hubble parameter is unstable in the future. So it's kind of like an ABC alternative. And you can see from this calculus graph of z and h of z that if you imagine different kinds of futures, you will have different extrapolations to z is 0. So in the case of the blow-up, definitely then lambda is dynamic. You have the largest h0. If lambda is constant, so you approach to de Sitter, which of course is the ideal ΛCDM, you'll be in along the blue curve B, and that will give you a slightly lower h0. And then of course if you go to Minkowski C, which was a proposal some years ago, also advertised by Mager in several papers, then lambda goes to 0 essentially. Then you have the lowest h0. Now the last one you can definitely rule out by the data. I won't talk about it here, but you can look at the deceleration parameter and it's just completely ruled out. So the question really is between B and A. So this is, for a theorist, this is a question on the stability of the vacuum. Is the vacuum truly stable? Is the Sitter realized in nature? And of course, this is a rich topic of discussion in string theory. Or is somehow, for reasons to be discovered, the vacuum unstable? And then of course you're in A. And that will definitely have an imprint on H0, basically on our H0 estimates as we do those today. But what is interesting is that this gives a natural discrepancy between A and B, that as you can see from this picture is probably going to be on the order of a few percent, which is sort of what we were talking about when we think about H0 tension as defined by the local distance tether and Planck measurements. Now, very recently, almost yesterday, this was announced at the Sacramento APS meeting last April. There was a first release of DESI, and they get very tentative evidence by binning their very large number of galaxy analyses for a dark energy, although that analysis was carried out in so-called ΛCDM, that they find evidence that perhaps this dark energy indeed is not constant. So this is quite interesting, although it's done within the context of ΛCDM, which is not a completely generalization of ΛCDM, that by such a massive approach, they find in their own way that dark energy is probably evolving. And another paper tightly related to this, I'm just quoting here a statement: DESI data reopen up the possibility of addressing the Hubble tension not only by an evolving dark energy, but perhaps also by late-time new physics. Now, this statement is very important, but also somewhat subtle, and that's what I'll talk about in this talk, how you consider potentially late-time evolution without messing up what is basically well established in early time cosmology. Another indication for late time evolution was reported in this work by Hu and Wang very recently, 2023. It's actually kind of a review that is based on their earlier work 1 year prior. You can see here various analyses of H0 that they argue by normalizing what is observed to the ΛCDM prediction that they find that the most striking departure from ΛCDM is actually a relatively low redshift. Okay, that certainly is consistent with what DESI is advertising based on their very large data set. So these are suggestions without any theory. And now I want to bring up the theory aspect. When you think about, and I alluded to this already on the first slide, when you make this proposition that the FRW is basically describing a conformal evolution of Minkowski, that is not in the natural language of general relativity. It doesn't, I mean, you can ask, is that a problem of general relativity? Is that a problem of our cosmology, or is it something else? Well, firstly, to be appreciated is that we don't live in Minkowski. We also don't live in de Sitter, because we have a Big Bang in a finite time in the past. And that means that any degree of freedom that you imagine is present in the universe will be subject to the uncertainty relationship. Because now you have to be careful about counting, how many degrees of freedom do we have. But certainly for each degree of freedom, you expect an uncertainty in energy that's essentially the Hubble parameter times the Planck's constant, a modulo factor of 2 pi. And if you were adding those uncertainties, so let's call this Q, then is the total sum over all the degrees of freedom in the universe within the Hubble volume times this uncertainty, you might get a finite background energy density. And this is inevitable. It's absolutely going to be non-zero. The question is this going to be consistent with what we have said so far? Now you can, first hint is you can work with canonical expressions. For instance, the Bekenstein bound that describes the total true number of degrees of freedom in the universe according to the surface area of the Hubble horizon. This, of course, is entirely in the spirit of black hole physics. So in that sense, we were in good company doing that. And you can also appreciate that perhaps the universe has a finite temperature. Although we don't live in de Sitter, maybe the de Sitter temperature is a relatively good proxy to the temperature of the vacuum. Of course, these are all practically unobservable temperatures in the sense of, laboratory temperatures. On the other hand, the associated energies being very small, but then at the face of the very large Bekenstein bound, then actually if you do form this sum, this n times epsilon, and you divide by the Hubble volume, remarkably, you get actually the closure density that we conventionally talk about as a classical quantity. In fact, prior to this, as you know, there is this so-called cosmological concept problem that says that if you don't follow the Bekenstein route, but you look at space-time as a classical four-dimensional primitive, perhaps, and you do an ordinary summation according to the rules of quantum field theory, then if you do the summation down to the Planck scale, you get this well-known divergence where you end up having a theoretical value that's 10 to the power 120 times the closure density that we observe today. Of course, there is a fundamental problem here, is that you assume that you have ordinary scaling of the total number of degrees of freedom according to volume, which is, of course, at odds with the scaling of the same according to surface area, according to black hole physics. So by doing, of course, this was done by Zeltowicz in 1967. This was prior to Bekenstein's work on black hole space-times. So there is potentially a fundamental issue here with the proper counting of and scaling with volume, that is scaling with volume versus scaling with surface area, of the true number of degrees of freedom in your vacuum. Now, if you continue this route, this classical picture, ignoring the Bekenstein bound, and you add to this, making it in some sense an unsolvable problem. If you look, for instance, at Weinberg's 1989 paper, then the lambda naught is viewed as being divergent in 1 over Newton's constant. This is not a very productive approach, because of course the challenge is to merge this or to harmonize this with general relativity, and general relativity is in G and C. It doesn't have H bar, so the problem seems to be rather to harmonize it in the limit of small h bar, not so much in the limit of small g. So another way to look at the same divergence is indeed to recognize that lambda naught is divergent in 1 over h bar rather than 1 over g. In other words, what do I need to do to allow h bar to go to 0 and get something that's consistent with general relativity? Well, that of course is in the spirit of what I just told you, of looking at the sum over small energies associated with the uncertainty principle. So now we're looking at a lambda naught that goes as 1 over h bar. And this, of course, then, if you want to merge this with general relativity, which is in G and C, you have to have some kind of a coupling that should scale as h bar to allow this to serve as a background energy density in the vacuum. Now, general relativity doesn't have a length scale, right? Because h bar doesn't exist in general relativity. There is no length scale in general relativity per se. So if you imagine regularizing this contribution 1 over h bar as a primitive to the vacuum of general relativity, you need a coupling that scales as h bar. And because there is no length scale in general relativity, you have to, of course, look at the solution in this case, which is going to then provide you with an h bar or 1 over h bar according to the area of the Hubble horizon. So you end up looking at a running coupling constant that is 1 over the area of the Hubble horizon in Planck units. So in other words, you're looking at a scaling or a coupling equation alpha p. AP is 1, where AP is your surface area in Planck units. That's dimensionless. And your alpha p then is going to be the inverse of this area. And if you apply this to the Hubble horizon, then actually your lambda regularized then by construction, alpha p lambda naught is going to be 2h squared over c. This is interesting because this is definitely allowed by general relativity. It's also not equal to 3h squared over c, which would be the de Sitter limit. So this tells you you're looking at a contribution of the vacuum that is agreeable to general relativity. It's not de Sitter, and it's dynamic. And of course, it will ask you to have an additional contribution from dark matter because you still want to have the sum of all the omegas to be equal to 1. Now, in today's age of precision cosmology, you have to have a full formula for the evolution. So you need to formalize things so that you can actually do a real data analysis. Just saying lambda goes as h squared, of course, is not good enough. And interestingly, you can get this from the path integral formulation upon recognizing that the propagator now, again in the absence of asymptotically flat infinity that I was referring to earlier on the first slide, you need to say something about your reference phase. You know, the propagator, as you know, is always something like e to the I phi. That's fine, but now, in the absence of asymptotically flat infinity, you have to say something about your boundary term. So that's a global phase reference, e to the I phi naught, that you have to borrow somehow from the Hubble horizon.
So what do you need to know? What's not phase? Normally we say phases don't matter.
Exactly. But here it's a background, not only you don't have infinity, so you cannot just stick in 0 there, but much worse, it's dynamic, because the Hubble horizon is varying in time. So if you end up borrowing it as a substitute for the absence of infinity from the Hubble horizon, your phi naught is going to be dynamic. So you should worry about it. Okay, then you can lay out various approaches, but the simplest approach is to then densitize this boundary term. So in other words, because you need to have an equivalent Lagrangian, even though this is a non-Lagrangian term. And you can do that by saying, okay, I'm going to replace my boundary term by a Ricci scalar that then depends only on the Friedmann scale factor. So it's going to be a non-local quantity. This is the typical engaging global phases. So that introduces ab initio one free parameter called little lambda which is some number, times the Ricci scale, Ricci scalar curvature expressed solely by the Friedmann scale factor. And I'm rewriting it here simply as little g times j, where j is a trace of the Slough tensor, which in 4-dimensional space-time is 1/6 times r. Okay, then if you fit to the data, there are many different arguments you can give, but the simplest is perhaps to just fit the data with an unknown lambda or an unknown g. You find that preserving the BAO and preserving the age of the universe, g is essentially equal to 1. So you might as well continue your discussion then that g is 1 and see what happens. Actually, I have general formula for general g, but since g is so close to 1, let's just see what happens there. Before I show you the analytic solution, let's just compare notes. So, since now we can actually talk about lambda CDM and the new approach side by side. So J as lambda is effectively saying we are freezing the dark energy. That's what you do in lambda CDM. You just take it to be some constant. And whereas, of course, in the previous approach, I highlight that this correction by this boundary term, this gauging of a global phase, inherently looks at lambda being dynamic, in which case then lambda is equal to j according to the previous description. So what is it? Is it frozen or is it dynamic? That's the question that is a reformulation of the problem at hand. So the first one, with the dynamic, gives you this analytic formula. You can add curvature here, and you can add different g's. It just makes the formulas more complicated. So here I wrote the solution for the Hubble extension in terms of matter density and radiation density. Those are the two, in a 3-flat background, so omega lambda is implicitly included. So those are the most relevant densities if you study the background cosmology, starting from the radiation-dominated epoch. And then you can look at this side by side in, of course, the same parameters with lambda CDM. As you can see, these are the same different formulas with the same parameters. The parameters, of course, will have slightly different values. But if we do a fit to the data, we will discover then differences. For instance, in particular, if I insist that nothing is changed in the Big Bang nucleosynthesis and the BAO, then it immediately follows that the Hubble parameter in the JCDM approach will be the square root of 6/5 times the Hubble parameter in lambda CDM. And that's interesting because this predicts then a tension between the two of 9.5%, which of course is exactly what is observed. So the way I obtain, and you can also think of this as an independent verification, is by insisting that the BAO angle, as determined by Planck, is preserved, is 1.04 radians times 10 to the minus 2. And you can basically then take the ratio of radiation to matter density from Planck, so you just keep everything the same in very early universe. Then you obtain what I just mentioned. You obtain this slightly higher value of H0 while preserving actually the age of the universe, the astronomical age of the universe, which is...
But I'm still missing where the difference comes from. You said you go from j to lambda equal to j, which I just want to see what that actually changes. So when you say j equal to lambda, you say in the de Sitter space, I know the entropy of my de Sitter horizon. I'm gonna define j from there. Okay. Now in the converse case, how do you know how j evolves with time? There's an equation for j now.
Yeah, I have an equation for j, for lambda. I take lambda to be j in the new approach, and j is 1 minus q h squared. It's dynamic. Q is the deceleration parameter, and h is the Hubble parameter. So in the radiation-dominated era, q is 1. You're not doing anything, it's just 0. But of course, all of this is inherently dynamic over the rest of the evolution of the universe.
In a pure de Sitter, what's q?
This model is an important point, as I argued just now. the pure de Sitter case is not included in this approach, it's excluded. So a constant h is excluded in this model, it's not allowed. That's why this model will put you on the track A. So there is no homotopy, if you like, to lambda CDM. This is different from W lambda CDM, which is a regular perturbation of lambda CDM. This is not a regular perturbation of lambda CDM at all. It's very close to lambda CDM for most of the evolution of the universe, but as you go to low z, less than 2, then discrepancies appear. Okay, if you like, I can go to my extra slide for a second. You know, the evolution is more like this. You can look at the J parameter, for instance, right bottom, and you see that, as you know, J is 1 means you're at lambda CDM. But as you go to very low, then all of a sudden J departs from lambda CDM. And that is a signature of putting yourself on track A, not on track B.
Excuse me. Can you hear me?
Yes, I can hear.
Hey, Maurice. I'm Tepe. So, sorry, I have a quick question. So, in this JCDM, how the curvature appeared in your expansion rate?
The curvature?
Yeah, omega k.
Oh, no, it's still 3 flat.
It's flat.
Yeah, 3 flat. Yeah. K is 0.
Okay, so even though omega m is less than unity, still it's flat.
Yeah, it's a 3 flat universe. The sum of omega matter, omega radiation, and omega lambda is 1.
Okay, thanks.
Okay, it's not lambda CDM, but it's very close to lambda CDM, except when you go to very low z. Then there are differences.
It's close to lambda CDM and lambda is small.
Eh?
You're close to lambda CDM and omega lambda is small.
Yeah, but omega lambda is not small when z becomes small. So if we look at things numerically, I mean, there are many, many ways now, because we are comparing apples with apples. So you can just look at any kind of data that is commonly used. You can check against the local distance ladder, or you can check the scaling that's predicted by the theory. Of course, you can also compare the lambda with CDM applied to CMB, and so on. So what you find here, so firstly, we are predicting the H0 at z is 0 upon fitting the BAO. This is very unusual. We fully, respect early universe, and then you get a new value for H0 today. If you just do a fit to the local distance ladder, you get about 74, 75. I mean, this is based on fitting of Farouk data. That's the small table of 32 values of H and C. So the uncertainty here is quite large. If we fit to the BAO, which of course is much better data, then you get 74.7. And of course, the local distance ladder itself, according to Maurice, gives you 73. And then if we compare also by simply using this scaling law, square root of 6 over 5, then we get 73.79. So this is completely consistent with what is actually independently measured by Reese in the local distance ladder. Note also that my matter density is somewhat lower than the usual lambda CDM matter density, which is interesting in discussions on S8. So if I give an overview in this plot of H0 vertically and omega m0 horizontally, you can indicate the various results known and new. And the little red box, of course, is the lambda CDM prediction, a relatively large omega m0 and a small h0, and all the rest is in green, say Reese, and then yellow and purple and blue are all the other estimates based involving JCDM. So in other words, I recover the existing tension between the local distance ladder and Planck through or in JCDMs. Now, an interesting other quantity is the deceleration parameter, already because J depends on the deceleration parameter, right? It's 1 minus Q H squared in the trace of the Stoughton tensor. Then actually, from the scaling laws, you can make a prediction for the deceleration parameter. It's no longer going to be roughly minus 0.5, which is the canonical value that you get from Planck, but it's more like minus 1. In fact, you can be a bit more precise because of these scaling laws. You get minus 1 point, basically minus 7/6, so minus 1.16. Now, interestingly, there is an analysis by Camarana and Valerio 2020 that obtain, I mentioned it in the middle in the table, LDLC, and they obtain minus 1.08 plus or minus 2.9. Of course, the 2.9 stands for the notoriously large uncertainties in measuring Q0 because it's one higher derivative, so it's much more difficult to measure than H0. But it is certainly suggestive that this Q0 may in fact be fundamentally different from the minus 1/2 in lambda CDM, and more like roughly minus 1. So again, I made a similar plot here, H0 and then Q0 horizontally, and again you find this tension in Q0 between the local distance ladder and JCDM versus Planck. Now, this serves, of course, as a background of anything else in the universe which evolves on a sub-horizon scale. So I thought I would add a few more comments on this because it pertains to the nature of dark matter. And one of the questions, of course, is what's the potential mass of the dark matter particle? So we're all familiar with pictures like this. You know, you started with the Big Bang, then you had a surface of last scattering with a fingerprint of the first inhomogeneities, and that then later, or maybe sooner, gave rise to the first galaxies and stars. So in lambda CDM, this happened at was expected to be 1 gigayear after the Big Bang, but James Webb basically upended this idea by showing that there are already plenty of galaxies when the universe was just a few hundred mega years of age. So roughly 5 times sooner than what is predicted by lambda CDM. Now, another reason I bring this up, because it's a very amusing topic actually, because this is, if you like, generating wild ideas just like dark energy is generating. Of course, this is much more recent. But some people go back to this idea that perhaps we can explain this by playing with time. Of course, playing with cosmic time is very dangerous because then you tend to mess up the DAO and things of that nature. But if you ignore all of that and you allow yourself some free speculation, you might consider, say, varying the fundamental constants. That's, of course, also very dangerous because fundamental constants are not fundamental only to cosmology, but also to biology and who knows what, chemistry. Anyway, people do elaborate on this. And there was some interesting work recently by Gupta, who then estimated that the universe better be 27 gigayears old, otherwise he can't explain James Webb Impossible Galaxy. But it's an interesting question. What would be physics-wise fundamentally wrong with this picture? That's not so easy to answer. I mean, you can have an opinion, I don't like this theory, therefore I'm not going to be using it. But it's another level to say what is actually really going wrong and what kind of contradiction do I get if I were to follow this. And this idea, of course, is very old. It goes back to Dirac, who was already in 1937 contemplating that perhaps there is a correlation of fundamental constants to background cosmology. But now we are in our picture now is somewhat enriched. We don't not only have fundamental constants, but we also have black holes. And we have entropy of black holes. So you can ask what happens to the entropy of the black holes if I play with these fundamental constants. Well, it turns out if you take the canonical relationships for the black hole entropy, then of course it has a dependency on the fundamental constants. But then if you look at this recent proposal by Gupta on a covariant with cosmic time, of the Newton's constant velocity of light, the Planck's constant, and the Boltzmann constant, then actually, following his recipe, you find that the entropy of the black holes is decreasing in time. Well, then you get a picture of something like this, where the universe, we included, is evolving forward in time, but according to his theory, then the black holes are moving backwards in time. So I find this an interesting contradiction, or if you like, an impossible solution to the impossible galaxy problem. So what then can be a candidate for this? So presumably then, these galaxies actually form earlier because they form faster, not because they're stretching time at some early epoch. Now it's a bit of a technical discussion, so I'll be a bit brief about this, but you can show that there is an acceleration in the formation time of the first galaxies through the process of gravitational collapse that scales with the same Stoughton tensor to the power 1/8. And of course, the Stoughton tensor was much larger earlier in the universe because the Hubble parameter was much larger. So this means that you can predict that by redshift dependence, the early formation was about 10 times faster, order of magnitude, than what you expect in ordinary ΛCDM. So in other words, this points to a relatively short time scale of gravitational collapse and hence the early formation of the first stars and galaxies. But interestingly, it's because of sensitivity to the background cosmology parameterized by this J. Now the same short time scale, of course, we also find the galaxy rotation curve. After all, the idea of radial acceleration is pertinent to gravitational collapse as it is, of course, in rotational galaxies, same physics. So here too, you have to make a confrontation between what you expect based on Newtonian mechanics, if you like, ΛCDM galaxy models, and what you get by a finite sensitivity to the background cosmology of your dynamical evolution. So this is known as observationally as the Tully-Fisher relationship, or if you include the variables that are like Tully-Fisher relationship. And that has been very well established by now, that you get this non-Keplerian correlation between mass, baryonic mass, and circular velocity. It doesn't follow Kepler. It's all either you have some dark matter or you have some anomaly in the dynamics. Of course, if you apply this to the James Webb Impossible galaxies, you're in trouble because their dark matter is omega m is already 1 in your universe. You're not going to be saving this by adding more dark matter. You'll need something else. Anyway, now you can go back to your classic books on mechanics. You know, which of the 3 Newton's laws is here perhaps at play in ways that we haven't foreseen. So, since Newton's third law is conservation of total momentum, you probably don't have to mess around with number 3. Number 1, of course, is if you don't do anything, that's not that here we are subjecting particles to forces. So that leaves the Newton's second law. So imagine then that we have, instead of for a given force, according to Newton's force law, Gm over r squared, perhaps then the response to this force in radial acceleration is not as we expect. Maybe we're looking at a larger radial acceleration in light of perhaps a very reduced inertia at play at these very small accelerations that are canonical for galaxy dynamics, you know, roughly in the order of 1 per second squared. In order then to account for the discrepancy of observation versus expectation, where expectation refers to the Newtonian model. Now, if you make a confrontation now between observations, in this case the spark data in red, and the ΛCDM galaxy models here in blue, you get this picture. This is a normalized picture where horizontally, basically, I plot photometric data, the expected Newtonian acceleration relative to the background de Sitter acceleration. And then vertically, I plot the Newtonian, i.e. the expected radial acceleration over the observed radial acceleration. As you know, galaxies rotate faster than you expect, so this ratio is less or equal than 1. But what is interesting is that is you see a marked discrepancy between red and blue. The red is definitely above the blue, especially when the acceleration crosses the de Sitter scale of acceleration, ADS, seat down to Hubble parameter. And this discrepancy is not small, it's essentially 6 sigma. And then as you go further out, you're essentially moving into the regime of weak gravity, parameterized by the baryonic coefficient relation, or typically the Ilgren's law, that says that the actual rate of acceleration goes more like the square root of the expected acceleration. So you get instead of 1 over r squared, you get 1 over r. That, of course, has its own parameter, a naught, because, of course, taking the square root of an acceleration, generating an acceleration means you have another acceleration in the square root. And then you, again, just for brevity of the presentation, I want to just simply mention that, again, this depends on J. So this recurring, that this dynamics also in this respect is sensitive to the background cosmology. And interestingly, this transition across the de Sitter scale of acceleration is important because it happens at a coordinate space at a transition radius of on the order of 5 kiloparsec. Now imagine, which is what of course ΛCDM galaxy models do, you take an n-body simulation with your putative, dark matter particles. Of course, that kind of n-body simulation will always generate a smooth distribution, despite diffusion. And of course, that can never produce something that looks like essentially a C0 transition, a very sharp transition that essentially is continuous but discontinuous in the first derivative across this de Sitter scale of acceleration. So if you want to preserve this, then it better be that the Broglie wavelength of your dark matter particles must be greater than this transition radius. So galaxies have anomalous dynamics because of some reduced inertia, but that's independent of every dark matter. The dark matter should not affect that, because otherwise you would make a smooth distribution. That's not observed. Well, if you impose this condition, then the de Broglie wavelength has to be essentially less than 3 times 10 to the minus 21 eV. And that actually is interesting because people who were studying fuzzy dark matter have been advertising, dark matter particles of a mass of 10 to the minus 22 now for quite some time. So I would subscribe to that idea that indeed the dark matter particles are ultralight of the same mass. Okay, so let me just conclude this presentation that we have a new Hubble extension with no free parameters, ΛCDM beyond ΛCDM, that is essentially derived from consistent IR coupling to the bare cosmological constant, which I refer to as the primitive lambda naught, because it scales as 1 over h bar. I'm also saying that because there is a second primitive, which I didn't have time to talk about. So the idea that you define primitives as bare quantities that go as 1 over h bar that have to be somehow coupled to general relativity is canonical feature. And that, of course, requires an IR consistent coupling that seals as h bar. So this lambda naught then is not a crisis, but it's actually a pillar of the vacuum in Big Bang quantum cosmology, because it allows you to derive J being the 1 minus QH squared. And as a result then, if we go back to this Friedmann equation, you note that this little lambda being now J, I'm correcting the Blackboard discussion, is no longer a constant, but because of Q, the acceleration parameter is actually second order in time. So the Friedmann equation, from a mathematics perspective now, is no longer first order, but second order. That's, of course, a hugely fundamental distinction between the two. And that allows you to resolve this tension between the local distance letter, what the local distance letter measures, and what is measured in early time cosmology through your ΛCDM fits, defined by the Big Bang nucleosynthesis and the VAR. And this prediction is very quantitative. The tension is essentially square root 6 over 5. And then an interesting spin-off is that you can infer that the dark matter particle is actually very, very light. Ultralight particle that is not going to be detected in the laboratory, etc. Okay, so I'll be happy to express. Yeah.
Okay, I'm sorry. I was late to ask questions. But can you write down an effective degree state for your model?
Yeah, you can define a W.
Yeah. And do you have a plot on it?
I'm sorry?
Do you have a plot?
Yeah, I do have a plot. I'll set the formula if I recall
That would
correctly.
be useful.
Yeah. We have in our PLC, when I was publishing with two string theorists, Calday and Partano, we have a formula for the W. I think it's 1 minus Q over 1 plus T2 or something. I have to look up the formula. It's a simple algebraic that's what. Yeah, it's an interesting question because what is remarkable is that, this is not the anticipator, just follow, gauging level phase, then you find that W indeed is 1/2 at method-dominated regime. So, when Q is 1/2, you get your W is 0. So you get exactly a method-dominated epoch in this cosmology. Yes.
One of the issues that I see as not fully quantitative in black hole thermodynamics is the back reaction of radiation on the space-time itself. Whereas this, I think, explicitly relies on understanding that back reaction.
Yeah, that's correct.
You're taking vacuum energy and you're assuming that the equation actually still holds. Which holds.
Actually, I'm not quite sure I totally agree because it's actually looking at, it's an interesting point of discussion. It's not so much the radiation, it's that you have the same formula for the closure density. So the closure density, if you don't express it in 8, but in 1 over R8, then you can compare nodes. The black hole, R8 of the horizon, here R8 of the Hubble horizon. Then you have the same formula for both. So would you call that a back reaction? I would call it fundamental to the energy density that defines a black hole, and here that defines the entire space-time with the cosmology.
Are you familiar with the Stone Page's analogy of the Sejong black hole spacetimes? So there he embeds, there's a black hole in a distiller background.
Yeah, you can do that, yeah.
And then of course you can tweak the scales, and if you make the mass comparable to the horizon of the distiller, then on the inside of this, vice versa, we can cross over, and of course at the cost of a point get the same formula as we have to be numbers go ahead. And in that language I would have said that you do get a continuous, it's not just an analogy, it is a one-to-one map between the distiller radiation and the Hawking radiation.
Yeah, you have to be very careful with this. That's a very good point. I recently, since a year ago, had several discussions with Pierre Legouf on this concerning the double Hawking temperature. Maybe you're familiar with this problem that he introduced in 1984.
I mean, the Tooth introduced.
Tooth introduced, yes. Actually, I just published a letter on this best quantum gravity. It's a fascinating puzzle. And as a conclusion is that, firstly, the topology of your black hole horizon is P2, and in the sitter it's S2. And as a result, for the black hole, you have to make a distinction between the temperature of the space-time and the actual temperature in the electromagnetic radiation. And that's because the emission is an entangled two-photon emission process for the black hole. There's not a single photon emission that Hawking introduces. After all, black hole is not a baryonic object. It's very similar to black body radiation, but it's not identical to black body radiation, because ordinary black body radiation is indeed random. But for the black hole, I find that the emission is an entangled two-photon emission there. So there are differences, starting with topology. It's not so relevant here.
But just to go back to what goes into these equations. So just go back to normal black hole evaporation. You say, well, certainly from far away, classically, energy presumably is conserved, so photons come out, so the black hole had better shrink. Like that's the logic that goes in, and I think that's the only game in town. Nobody's got a better explanation as to what should happen. Even though microscopically it might be hard to pinpoint why exactly that should be the case. So now, again, I would have said on Page's language, in his thought experiment, he says, well, you can play these games. I can embed a black hole in a de Sitter space-time. And if the black hole is smaller than the universe, which in our universe would be the case, our black holes that we see obviously are smaller than our universe, and the temperature of the black hole is higher, and therefore the net radiation direction is from the black hole out. But of course, the temperature of the de Sitter is higher, the black holes will grow. Okay, so he talks about the thermodynamics of the coupled de Sitter black hole system. And you can make one grow, the other grow, there's equilibrium, but unstable equilibrium and makes to equal, and therefore they reach the same temperature. And I just feeling that this is well related. It touches upon many of the same points. But then if you have to ask, well, if you know, like on an equation of motion, I do think it implicitly it does say that, this back reaction is understood in the sense that you can take the expectation value of these temperatures.
Yeah, I mean, you can certainly highlight more like that in this context, one is emphasizing that the background vacuum is a finite temperature. But in GR, you would naively assume zero temperature, less cold, And in this case, just like in the black hole case, one is saying, it's not zero, you have to be careful because there's a finite temperature. So that is a common denominator here. So also cosmologically, our vacuum has a finite temperature, and that of course means that it has a finite energy density. So you can rewrite things, articulate things in that language, definitely. But the result mathematically is that your first Decon equation, no matter how you phrase it, physics is the same. It's going to be now second order, more first order. So you get fundamentally different solution, even though for most of the universe it looks very much the same. Yeah.
So in JCDM model, you do have a different redshift dependence of Hubble parameter compared to ΛCDM, as you showed. Does that imply that these energy components in the Hubble parameter evolves differently from ЛCDM? Because you do have different Z power. Does that imply these energy components are evolving in a different rate in time?
Well, I mean, your geometrical corrections observation are the same, just your parameter history is slightly different. That's all.
Oh, okay. So it's not about like their physical evolution.
That's right. That's okay.
And do you have any guess on SA tension?
Yeah. So I didn't mention it too much. I personally like that. I mean, ideally, we have to do a little bit more homework by doing full fit to see the things of that nature. But prior to that, from the table I showed, I do get a lower matter density, and that's definitely in the right direction. As you can see, my matter density is more like 0.26, 0.27. That's very advantageous for it using S8. Of course, S8 is not just matter density, it's sigma 8 times the square root of matter density of 0.3. So if sigma 8, for instance, doesn't change, then you solve the S8 tension. But you have to do a self-consistent calculation to substantiate this. But definitely, the tension is reduced. Whether it's fully alleviated, it's possible because the tension is not so large. But certainly, this is absolutely in the right direction. Because your prediction with ΛCDM is too high. So if you reduce matter density, your potential maybe good step.
Okay, then do we have questions from online participants? If not, we can thank our speaker today. Let's give him a applause.